What would it be like to live on a planet where every step feels like carrying the weight of the world on your shoulders? Over the years, we've explored the possibilities of settling strange new worlds, from the low-gravity plains of Mars to the weightlessness of space stations. What about the heavy hitters of the cosmos, planets where every step feels like lifting a boulder? Today, we dive into high-gravity worlds. What would life in a high-gravity environment be like? What are the planets like? Those are questions that often come in mind as we continue discovering large exoplanets bigger than Earth, rather than Earth-like or smaller ones. It's a big range, especially as we'll cover super large planets too, and also briefly visit non-planet cases like white dwarfs, so there's a lot to discuss today as we visit high-gravity worlds. And thus a drink and a snack might be in order, and don't forget to hit those like and subscribe buttons. From the outset, we need to recognize that life on a high-gravity world would be rough for you and I. On a high-gravity planet, even lifting a cup of coffee could feel like an Olympic event. If that's the case, I would finally have the biceps to match my caffeine addiction. Science fiction often portrays inhabitants of high-gravity worlds as muscular, stocky, and resilient. Think Tolkien's dwarves but with a sci-fi twist, like the leaves of Votan from 40K. While this image is captivating, how realistic is it? And what would life be like under such crushing gravity? In the reverse, folks living in low or no gravity are often slender to the point of stick-like and tall. Today, we'll ask how realistic those portrayals are, and we'll see that, like a lot of things in sci-fi, plausible but with some caveats. Before we discuss whether we could live on higher gravity planets, we should first ask if we would, why we would, and how common such places are. High gravity worlds aren't just theoretical curiosities. They could offer unique resources, environments for scientific study, or even unexpected havens for life. Larger planets clearly are not rare, after all we've discovered so many of them. However, that abundance can create a misleading impression of their frequency. Larger planets are easier to spot because their immense gravity tugs on their stars, causing a wobble, or they block more light during transits. These detection methods mean we see more of these giants, but that doesn't mean they dominate the cosmos. It's like spotting tall trees or mountains in a landscape. While they're easier to see, there are far more blades of grass. Still, those trees or mountains hold vastly more total mass than the grass. Celestial bodies are similar. Larger ones are far less common, but contain far more total mass. For instance, stars smaller than our Sun are far more numerous than larger ones. You'll find stars as small as 1/10 our Sun's mass, the minimum for stellar fusion, and others more than 20 times our Sun's mass, massive stars that barely last a million years before exploding as supernovae and collapsing into black holes. These massive stars are also 1,000,000 times brighter than the Sun, and 1,000,000,000 times brighter than the dimmest stars, making them far easier to spot. This is why we originally classified the Sun as a yellow dwarf star, back when we could only observe the brightest or closest stars. Later, we realized at least 95% of stars are smaller and dimmer than our own Sun. We cannot thoroughly catalog anything smaller than Earth outside our solar system yet. However, based on what we see in our own system, there is generally an inverse relationship between size and quantity. The smaller the objects, the more there is. Most of the mass in our solar system is concentrated in its largest objects. The Sun accounts for 99.8% of the system's mass. Of the remaining 2/1000ths, more than half of it is in Jupiter. Of the remainder, most is in Saturn, and of what's left after that, Uranus and Neptune split almost all of it. Earth and Venus each make up more of the remaining mass than every other object in the solar system combined, from Mars to the many moons, to comets, asteroids, and even specks of dust and gas. That is likely the case in most places, but even if we're not an outlier, we're probably not the norm either. And it's not a static situation. Large planets tend to retain their mass or even grow by absorbing other rocks, while stars lose mass through fusion and solar wind, but also gain it from objects falling into them. Medium-sized asteroids get split into smaller ones by collisions. Our solar system contains over 1,000,000 minor planets, most without names, and that number is probably much higher than it was in the early days of the system. The irregular shapes of many asteroids and smaller moons aren't just a result of their lower gravity. They're also fragments from impacts that shattered once larger bodies. It's not just that high-gravity worlds are far less common than smaller ones. Common or not, there are still plenty of them. What really matters for habitability is the aspect of their mass, as it often leads to very thick atmospheres. Larger ones might also retain significant amounts of hydrogen or helium in their atmospheres. Understanding the rarity and challenges of high-gravity worlds helps us imagine how life, or we, might adapt to these colossal conditions. As we discussed before in our episode on Hycean planets and the Fermi paradox and gravity, planets more massive than Earth are very likely to be utterly drowned in their own oceans. This is because planets with higher gravity retain hydrogen more easily, likely have stronger magnetospheres, and tend to have more water relative to their total mass. Doubling a planet's mass might result in tripling its ocean volume. However, a planet twice as massive as Earth is only about 26% wider and 59% larger in surface area. This means that even if the water volume were proportional, oceans would be much deeper. If the water volume tripled instead of merely doubling, with only a 59% increase in surface area, ocean depths would increase by 89%, almost double. Considering Earth's oceans average 3.7 kilometers deep, this would add another 3.3 kilometers, leaving just a few small islands above sea level, with few wide or tall enough to form large land masses. Higher gravity also limits volcanic eruptions, and combined with increased erosion caused by raindrops falling with more force, dry land becomes even harder to sustain over time. Additionally, higher gravity planets have thicker atmospheres. On Mars, achieving Earth-like air pressure requires more air per unit area, because lower gravity pulls the air down less, resulting in reduced pressure. On a higher gravity planet, the reverse is true. Less air is needed to achieve normal atmospheric pressure, but we would still expect a greater total mass of air due to the same factors that increase water retention. This also contributes to erosion, making dry land even scarcer. For these reasons, we assume dry land is less common on more massive planets, and oceanic life is sparser. This is because such life cannot rely on photosynthesis to power ecosystems and food chains, as the lack of shallow waters to mix nutrients with sunlight limits productivity. Ecosystems would likely be restricted to geothermal vents deep under the sea as their primary energy source. Between scattered small islands, if any, and limited geothermal oases on the seafloor, ecosystems would be shallow, and Foster's rule, or the island effect, would likely apply. This could limit how large creatures can evolve, potentially affecting the development of large brains. However, islands can also encourage gigantism and low predation, offering pathways to larger brains. While I tend to associate larger brains with fierce competition and predator-prey feedback loops, it's unclear if this is strongly supported by data on Earth, let alone other planets. On high-gravity planets, I'd bet on dwarfism dominating, as life on land would require much sturdier skeletons. The proportion of an animal's body mass devoted to its skeleton increases as weight does, as a consequence of allometric scaling. Allometric scaling, which describes how proportions change with size, plays a significant role here. For example, as weight increases on a high-gravity planet, the proportion of an animal's body mass devoted to its skeleton must also increase to support that weight. This principle deviates from isometry, where size scales uniformly. Galileo, best known as a founding figure in physics and astronomy, also ventured into biology. In Dialogues Concerning Two New Sciences, he observed that mammals' skeletons become disproportionately stronger and more robust as their size increases, a necessity for supporting their greater mass. This is probably the best case for dwarfism on higher gravity planets. Being smaller means you need less bone mass, and counteracts the need for higher bone mass for high gravity. Needless to say, more gravity does mean more muscle, or some cybernetic enhancement perhaps, if you are to thrive or even survive. Gravity shapes planets, stars, and even the possibilities of life itself, and the civilizations that might arise from it. In much the same way, our search for knowledge has shaped our civilization, so what would happen if that search concluded? In The End of Science, our Nebula exclusive episode, we examine whether science itself has a final frontier. Could there come a time when every question is answered, every theory proven, and every discovery made? And if so, what happens next? Find out in The End of Science, available now exclusively on Nebula. Nebula is the largest creator-owned streaming platform, featuring early, ad-free access to every SFI episode, along with exclusive content from myself and other fantastic creators, like Real Science, Real Engineering, and Stephen Milo, and check out Nebula originals like Faithless, A Sojourn Story, a tale of humans surviving in the cold depths of extragalactic space in a distant and harsh future. Sign up at go.nebula.tv/IsaacArthur using my code IsaacArthur to get 40% off an annual plan, $3 a month. Nebula also offers lifetime memberships and gift options, so you can share exclusive content like The End of Science with friends and family. And for new Nebula subscribers, you can get access to guest passes. Share your passion for Nebula with friends and family. With them, they can get free and easy access to all Nebula content for a whole week. So go subscribe to Nebula and give a week of exclusive content with guest passes using the link below to get 40% off the annual plan. And now, let's get back to the crushing reality of high-gravity worlds, and how to make them more livable. Though we cannot assume alien life would use the same material for bone or muscle, they might get way more power out of some muscle equivalent they had evolved. Maybe they found a way to use aluminum for bones. This idea that higher gravity requires stronger or smaller structures doesn't just apply to biology. It's the same principle that drives how we design skyscrapers or spacecraft, and thus how civilizations, be they native or arrived by spacecraft, might settle such a world. Taller buildings need disproportionately thicker supports, and larger rockets require more robust structures to withstand stress and would launch less into orbit because of the higher orbital speeds required from the gravity. On high-gravity worlds, life forms would be subject to similar constraints, evolving sturdier skeletons and perhaps sacrificing agility or speed for stability, or simply not getting very big, which again the island effect would seem to support. But what if evolution found other ways to adapt? Could creatures develop lightweight, composite-like biological materials, akin to carbon fiber or aerogels, to support their mass without needing thicker bones? Or could entirely new skeletal structures emerge, such as hydraulic systems, or external armor plates resembling exoskeletons in insects or crustaceans? These adaptations might result in forms of life unimaginable to us. This line of thought also raises questions about whether intelligence could flourish on such worlds. Would heavy gravity environments slow the pace of life, leading to less dynamic ecosystems? Or could the challenges of survival, coping with immense pressures, limited land, and scarce resources, drive innovations and new evolutionary paths? Once again, it seems likely that more massive planets would have less dry land. In our Fermi Paradox Air episode, we explore the idea that even Earth might be too massive to avoid submerging its land under vast oceans and thick atmospheres. Earth's history offers an interesting twist. The Moon is thought to have formed from a collision between Earth and a dwarf planet, stripping away much of its early water and atmosphere. Without this event, Earth might have had far more water and air, possibly of a very different composition. Furthermore, Earth's remaining water and atmosphere are believed to have come from a heavy period of cometary bombardment, possibly caused by Jupiter migrating. Needless to say, all three events are extraordinary and might not be typical, making Earth a poor baseline for estimating how other planets form in terms of sea and sky. On larger planets, catastrophic events could strip away vast amounts of water and atmosphere. A collision with a dwarf planet or a massive asteroid could significantly alter a planet's composition. Proximity to a brighter, hotter star could amplify atmospheric stripping, as higher levels of UV radiation and stronger solar winds erode the atmosphere more aggressively. These effects become more pronounced with increases in stellar mass, where solar wind output rises sharply. Planetary migration might also play a role. Massive planets, potentially as large as Neptune or Uranus, or even larger, might have formed close to their stars, where intense radiation stripped away lighter elements like hydrogen and helium. As these planets migrated outward, they could be left with a rocky core, several times Earth's mass, with more modest oceans and atmospheres. In binary systems, an orbiting planet could have its atmosphere and oceans stripped away by the larger companion during its red giant phase. The material ejected during this phase, rich in carbon, oxygen, and nitrogen, could later enrich the smaller star's planets, potentially allowing the stripped planet to recover its seas and sky. Such a planet, initially reduced to a scorched husk, might undergo a second chance at habitability after the larger star cools into a white dwarf. Stars with masses as low as 4 solar masses, quadruple our Sun, which live for about 1 billion years or less, can provide sufficient time for life to emerge on such planets. This suggests that revived cinder planets need not orbit dim, long-lived stars to allow life to develop. In fact, an even larger binary companion could end its life as a supernova, not only scouring the planet clean of its sea and sky, but also enriching the surrounding system with heavy elements essential for life. This opens intriguing possibilities for planets shaped by dramatic cosmic events, potentially creating worlds where life could flourish under unique and extreme conditions. So, what are those intriguing possibilities? Counterintuitively, flying creatures on high-gravity planets might not struggle as much as you'd think. While high gravity creates challenges, a denser atmosphere could provide more lift for the same wing area, and faster planetary rotations could generate stronger winds to aid flight. On such worlds, creatures might even evolve gas bladders filled with helium or hydrogen for buoyancy, enabling them to float and glide effortlessly. Picture vast drifting organisms with translucent bladders shimmering in the sky, propelled by wings adapted for maneuvering through dense air, possibly with long arms or tentacles for reaching down to trees or the ground. This adaptation is not limited to creatures. Human settlers might employ similar principles. This might include wearable technology or even genetic engineering or cybernetic enhancements. Buoyant habitats, like those proposed for Venus, could offer an appealing alternative to ground-level living, especially if surface conditions are extreme, with crushing atmospheric pressures or inhospitable weather. It's also important to consider how pressure gradients affect ecosystems. On low-gravity planets, gradual pressure changes allow ecosystems to thrive across a wide range of altitudes, from towering mountains to deep oceans. However, on high-gravity worlds, the habitable band is much thinner, compressing the range of viable ecosystems. This makes life more constrained and dependent on specific environmental niches. Life on a high-gravity planet would be extremely challenging for humans. Even without resorting to cybernetic or genetic modifications, we would likely depend heavily on powered exoskeletons to function. These would not necessarily need to be bulky or clunky. With advanced technology, such systems could be seamlessly integrated into everyday clothing, offering strength and support while remaining lightweight and unobtrusive. Another intriguing possibility is the development of anti-gravity technology. This could allow us to create localized regions of reduced gravity, functioning like domed habitats on airless worlds. Instead of oxygen-rich bubbles, we would have low-gravity towns nestled within a high-gravity environment, enabling more normal movement and reducing strain on the human body. For those wondering, while you can use spin gravity to simulate higher gravity on low-gravity planets, the reverse is not true, except in the special case of the equator. Here you could theoretically straddle the planet with a massive maglev rail and run a non-stop high-speed train, or even a chain of habitats around the planet. This concept leverages centrifugal force to reduce perceived gravity. Interestingly, this is essentially how microgravity works on space stations. They are only a few hundred kilometers above Earth's surface, where gravity is still about 90% as strong. The sensation of weightlessness comes entirely from their orbital motion. On high-gravity planets, such a system could take the form of a wide equatorial belt under a protective dome, which might serve multiple purposes. For example, the domes could create a vacuum for high-speed train habitats or help regulate temperatures on airless sun-baked planets by placing a shade or reflective surface above the habitable belt. Mining colonies could use this approach to remain shaded or cooled while spinning around the planet's equator, reducing the effects of extreme gravity. You could do this on great circle paths that weren't equatorial, but would need to either alter your speed based on latitude or accept a somewhat fluctuating level of gravity over the course of a couple hours, which is also what your daytime length would look like based on your speed. You are moving around that planet a lot faster than normal spin rates that control day length, and this might be another reason to have shades overhead and simply generate light under them as needed and proper. Angling your rings to non-equatorial great circles would allow many other rings of habitation at cocked and overlapping angles though. While the equator is the most practical location for such a system, it does not have to be restricted to it. Higher latitudes would provide less free rotational speed, and tilting the system at an angle introduces some engineering challenges, but both are feasible with advanced technology. Such designs could offer new ways to live and work on worlds that would otherwise be unbearably heavy. High gravity would likely limit how tall trees could grow, but we might see fascinating adaptations to overcome these challenges. Trees on such worlds might evolve new structural materials beyond cellulose and lignin, offering great strength with less weight. Alternatively, buoyancy could play a role. On planets where helium is abundant, this gas might be incorporated into the very bulk of trees, reducing their effective weight and enabling them to grow taller despite the heavy gravity. On the smaller side, high gravity could also influence the types of skeletons animals develop. On Earth, we rarely see large land animals without endoskeletons, while we once had much larger creatures with exoskeletons, like ancient dragonflies spanning a couple of feet. These larger exoskeletal species were likely outcompeted in their size niches by animals with internal skeletons. The reverse might be true on a high-gravity planet. The intense gravitational pull could favor internal skeletons even at smaller scales, making endoskeletons more advantageous than exoskeletons for insects and similar creatures. Such adaptations would allow for sturdier, more efficient support systems, reshaping entire ecosystems in ways that might look very different from those on Earth. We shouldn't assume that all high-gravity planets follow the same evolutionary paths. One planet might be dominated by creatures built like tanks, with turtle-like shells reinforced by thick layers of helium-filled chambers for buoyancy and protection. These slow, prodding herbivores could graze the land, moving deliberately to conserve energy in the heavy gravity. Alternatively, another high-gravity world might foster ecologies of small, fast animals. These creatures could be powerfully muscled to handle the gravitational pull, darting swiftly across the terrain or scuttling on many legs for stability and speed. The demands of high gravity might favor compact, efficient body designs capable of rapid movement despite the environmental challenges. Amphibious life could also be far more common, especially on planets made up of archipelagos rather than large continents. Water, with its natural buoyancy, might allow for larger-bodied creatures that would struggle on land. Such environments could lead to ecologies where life thrives both above and below the waterline, adapting seamlessly to both habitats and creating a fascinating diversity of forms. Indeed, we might see organisms, both flora and fauna, floating above the landscape using helium sacs, drifting reefs of ecologies rising up during the daytime to get sunlight, then sinking down to safety below the sea at night. I want to move on to more extreme scenarios, like life on a planet similar to Jupiter or even on stellar remnants. However, this becomes far more speculative territory. Gas giants like Jupiter pose significant challenges for life as we know it. There is no solid surface, and the conditions are extreme, with immense gravity, powerful radiation belts, and violent storms. However, some speculative scenarios suggest the possibility of life existing as floating organisms in the upper atmosphere, where pressure and temperature might be more hospitable. These creatures could resemble massive jellyfish or blimps, using gas-filled sacs for buoyancy. Rather than relying on sunlight, they might feed on chemical energy sources like methane or ammonia, much like extremophiles on Earth that thrive in environments devoid of light. Lightning storms on gas giants could serve as an energy source, with life forms evolving mechanisms to harness this energy, perhaps using conductive appendages or internal electrical gradients. The challenges, however, are significant. Immense gravity would likely limit the size of these organisms, and the turbulent winds and storms would demand highly adaptive and resilient life forms. Even more extreme is the idea of life on stellar remnants, such as neutron stars. These environments are among the harshest in the universe, with surface gravities billions of times that of Earth and immense magnetic fields. Robert Ford's Dragon's Egg imagines a unique form of life evolving on the surface of a neutron star. Such life would be composed of nuclei and particles bound together by nuclear forces, rather than chemical bonds. Their metabolism and reproduction would occur on timescales millions of times faster than Earth's biological processes due to the compact size and high energy density of these systems. Energy for life might come from the neutron star's magnetic field or thermal radiation emitted by its surface, with life forms adapting to feed on these energy gradients. On a neutron star, movement might involve manipulating nuclear interactions, and communication could occur through radiation bursts or electromagnetic pulses. The extreme gravity would confine life to a two-dimensional plane on the neutron star's surface, and the organisms would need to be unimaginably robust to survive the intense radiation and heat. While these scenarios remain purely speculative, they stretch our understanding of what life could be, challenging us to imagine entirely new biochemistries, timescales, and adaptations. Whether in the turbulent skies of a gas giant or the crushing gravity of a neutron star, life might find ways to persist in forms beyond our wildest imaginations. These extreme environments push the boundaries of what we consider possible, forcing us to rethink the fundamental requirements for life. And beyond the worlds we might encounter in terraform, adapting to giant planets could unlock vast stockpiles of resources. These colossal worlds may become sites for unique human habitats, such as diamond-hollowed domes floating deep within their dense atmospheres. Such habitats could harness the extreme pressures and exotic materials present in Jovian environments, turning challenges into opportunities. Additionally, living deep beneath 1,000 miles of atmosphere offers unparalleled protection and concealment. A civilization could effectively hide itself from external threats or cosmic hazards, shielded by the immense layers of a gas giant's atmosphere. Energy beams and even relativistic kill missiles would simply be soaked up by the sky above, allowing only smart and slow devices to hunt like submarine predators for hidden habitats. These hidden habitats could serve as fortresses, research outposts, bunkered archives, or even thriving communities, demonstrating humanity's ingenuity in leveraging even the most extreme environments to its advantage. We could imagine life evolving or adapting to survive on the black dwarf remnants of ancient stars, billions or even trillions of years in the future. The gravity on such objects would be thousands of times stronger than on Earth, making it nearly impossible for ordinary organisms to exist. Tiny life forms might require structures as robust as diamond for bones, and it's anyone's guess what materials could function as muscle to enable movement in such extreme conditions. Civilizations that once thrived on shells orbiting white dwarfs, as discussed in our episode Colonizing White Dwarfs, might gradually adapt over eons to inhabit the cold, dense remnants that white dwarfs would eventually become after the stars have burned out. Speaking of deep time and extreme environments, civilizations might also choose to live near black holes to take advantage of the time dilation effects, which dramatically slow down the passage of time. In a few months, we'll be exploring this idea further in our episode Galaxy-Scale Megastructures, where we'll discuss the concept of ultra-massive but Earth-like birch planets built around supermassive black holes. While it's possible to create Earth-like environments around smaller black holes by constructing a shell at a distance where gravity equals 1 Earth-g, time dilation of that range would be negligible. Similarly, you might build shells around planets like Saturn or Jupiter, or around other stellar remnants, at distances where Earth-like gravity could be maintained. Black holes themselves could serve as natural ports or capital systems for interstellar empires, as we proposed in Colonizing Black Holes. However, if you want to truly take advantage of extreme time dilation, you need to venture deeper into that gravitational well. You could imagine building additional layers of habitation, shells closer to the event horizon, where gravity is far stronger and time slows to a crawl relative to the rest of the universe. The universe offers an incredible diversity of environments, from planets with crushing gravity to the turbulent skies of gas giants and the unimaginably dense remnants of neutron stars and black dwarfs, and a vast supply of all of them, billions and billions of even rarer world types. Each of these worlds presents profound challenges, but also fascinating possibilities for life and civilization, if we are willing to push the boundaries of what we consider habitable. The adaptability of life and technology has always been humanity's greatest strength, whether building buoyant cities floating in dense atmospheres, crafting diamond-hollowed structures for extreme gravity, or engineering habitats to thrive in time-dilated depths of black hole gravity wells. Our ingenuity allows us to envision thriving in even the most hostile conditions. The cosmos invites us to explore these extremes not just to test our limits, but to expand our understanding of life itself. Perhaps the most intriguing thought is this: in adapting to such environments, we might not just survive, but evolve, creating new forms of life and civilization that are as alien to us now as we are to the first organisms that arose on Earth billions of years ago. Where there is challenge, there is opportunity, and where there is imagination, there is no limit to the future we might create.